Now most collisions occur in two dimensions, so you have net forces that act not necessarily along the coordinate axes. Okay, not all the net forces can act along the coordinate axes unless the objects collide head-on and continue to move on the same line, but perhaps in opposite directions. Okay, so we have now a situation where we've got to use vector forces. So the vector force, Fnet, times delta t, is going to equal the impulse. Now the force is given as 300 newtons times I plus 400 newtons times J. Excuse me, and the duration of the collision is given as 5 milliseconds, 0.005 seconds. Well then our we have a constant mass, so we make note that the change in mv is m times the change in v, since m is constant. So, and then we know that m delta v equals F net delta t, something I regarded as implicit, and then I later decided to sandwich in here. So if you can't read that, it's just m delta v equals F net delta t, but the delta v and the F are both now vector quantities, so we have arrows over the top of the two. So we can say that m delta v is what? It's your impulse. Now if we multiply 300 newtons times 0.005 seconds, we get 1.5 newton seconds, or 1.5 kilogram meters per second. And of course the 300 newtons is the coefficient of your I vector. That is, this is the I component of the force. So when you multiply by the 0.005 seconds, you get the I component of the impulse. Impulse is a vector quantity. Momentum is a vector quantity. Now, this contrasts with energy, which is not a vector quantity. Okay, you're squaring velocity. You're not getting a vector quantity when you do that. Okay, it was a little bit of a digression, but it should be pretty clear where the 1.5 kilogram meters per second comes from in this collision, in this calculation. And then the 400 newtons times 0.005 seconds is going to give you 2.0 kilogram meters per second, and that's times J. And there's the J. It doesn't look like much of a J, but it even has an arrow over it. Let's put a little better hook on it and maybe try to make the tip of that arrow a little clearer. Okay, so the impulse is 1.5 kilogram meters per second times I plus 2 kilogram meters per second times J. So what's our change in velocity? Well, mass times change in velocity equals the impulse. We divide the change in velocity, the impulse, by the mass, and we get the change in velocity. Now, I factored out the unit kilogram meter per second, which is divided by the kilogram, so I get unit meter per second. And then I just divide 0.1 into 1.5 to get 15, into 2.0 to get 20. So I have a delta V of 15 meters per second in the I direction, 20 meters per second in the J direction. Now our final velocity is our initial velocity plus our delta V, and we're given an initial velocity of 4 meters per second times I minus 3 meters per second times J. That wasn't written down here, I was out of space, but it's right there in your document. And if we add this change to that initial velocity, this is what we get. And actually, I think there was, no, actually I think I got it right. Okay. It was 4 meters per second times I minus 3 meters per second times J. That was the initial velocity. You add that to the change in velocity, you get this. So we get components of velocity. And in general, your impulse momentum theorem is going to apply in two dimensions. You'll have two components. You could even have three components in space.